Yes. Whatever you wear. Exams, homeworks. This is a very important concept, and we kind of devoted 20 minutes to it last lecture. I'd like to devote the entire lecture to it, so that you guys really understand it. And this is also your extra credit assignment for Lab 2. And it's a very fun concept. It's very powerful. And hopefully we will see this at the end of the lecture. It's very warm here as well. Okay. Maybe people heard what I said. They're just coming in. Okay. But before we start, a couple of announcements. We graded your homeworks. Well, I don't know if this is true at this point. Is it? Or it will be true. Okay, it will be true very soon. That was the goal. So these are speculative slides, if you will. They were written before we knew whether or not this was true. Currently, it's not true. So if you go and check Blackboard, you won't see your grades. But you will see them, hopefully, at the end of today. And we'll definitely distribute the homeworks next class. Lab assignment 1 is also graded. You can go into your hand-in directory. There's a grade.txt file, right, that you can look at. I don't know how detailed that txt file is. Is it detailed?
Yeah, it is.
Okay, it tells whether or not you failed or passed each test.
Yeah.
And each test case is also provided, right?
Yeah, they are released. Yeah.
Oh, okay, they are released. Okay. I was conservative in speculation here, and aggressive in speculation in the other slide. And this is your grade distribution. I don't want to dwell too much on it, but most of you did well. I think 55 of you turned it in, right? And 9 of the assignments were actually perfect, which means that they matched exactly the output we expected, and the ISA specified, hopefully, except for the branch delay slot. And several other of you were quite close. So, but if you're around here, well, if you have anything imperfect, I would strongly recommend that you go and fix your lab. You will learn from that exercise, especially since we provide the test cases now. And you can use your lab later on for debugging your other assignments. Well, we did something else here. Yes. Out of those of you who got it perfect, we also looked at how fast your simulation actually ran. Your simulator actually ran for a complex program that computed prime numbers, or
The sieve of Eratosthenes.
it does what?
The sieve of Eratosthenes, computing primes.
Okay, computing primes. And we timed your simulator, and I think there was a methodology behind it. You can talk with Chris about this. It's only a single benchmark. You may be performing better on other benchmarks, who knows. And one of you actually performed, these are rounded, so maybe it's not that big of a difference, but 3% better than the closest one. So one of you has the fastest simulator, and you'll get a prize for it. Hopefully in the next lecture. And my TAs will remind me to find the prize. Okay? We didn't specify this was a criteria, so this is not going to affect your grade significantly, but you'll get the extra prize. I guess this is essentially the execution time in terms of seconds. So there were quite a few students that took much longer than these. So I wonder what was the difference. Have you looked at the code?
What's the question?
So the question, this is 27 seconds, right?
Yeah, I don't know what was going on there.
Okay, whereas some of you were closer to 5 to 8 seconds. So there seems to be a design difference. That's my guess, but you can time and see. But in the next few assignments, we will actually try to provide optimization criterion for you so that you can optimize your design, for example, for the critical path. And we will look at different critical paths. These won't necessarily affect your grade. Your goal is really to get things functionally correct and not necessarily make things fast. But if you already made things functionally correct, making it fast is the next step. So hopefully this will give you some additional challenge in terms of doing your labs. It's a lot of fun, actually. This is really the trade-offs people make when they design simulators. Like the simulator you designed is actually an instruction set simulator. It models a subset of the MIPS instruction set. And accuracy is one of the first goals. There are two major goals in simulator design. How accurate is it, and how fast is it? In our assignment, the goal was really accuracy. That's what you will be graded on. But if you go out in the industry, for example, if you're working for Intel, AMD, or Oracle now, you will design a simulator for maybe x86 or UltraSpark. And you need to get the simulator accurate. If it models an instruction incorrectly, then you will get the wrong answer when you're designing your next generation processor. And you want it to be also fast, right? You don't want it to take, I don't know, hundreds of years to simulate a prime number testing program. Yes?
Will all the tests and British enough be released?
Yes, they're all released.
They have been, yeah.
Where are they?
They're in the lab/lab1.final test directory in the AFS space.
Okay, so we will put these up on the lab page, right?
Well, they have been.
Oh, they're already on the lab page? Okay, web page.
Oh, not on the web page.
Yeah, let's link them from the web page. Let's link the exact location so that everybody knows. Okay. So accuracy comes in two ways, actually. One is functional accuracy, which is what you were concerned with in this assignment, because you didn't do any timing, right? Your goal was to functionally model what the instruction does. So functional accuracy essentially does the simulator accurately model what the instruction set specifies. But there's another aspect of accuracy that you will see when you do your high-level simulation later on for pipeline processors and caches, and that's timing accuracy. In this case, we didn't model the timing, right? The simulator didn't try to emulate what would the processor do for each instruction, right? We didn't concern ourselves. Everything was one instruction at the instruction level. But you can design a simulator that models, for example, the microprogrammed microarchitecture that we started discussing. And in this case, timing accuracy means does the timing simulator accurately model how many cycles the hardware would take to execute the program. And you may be inaccurate. You may be perfectly functionally accurate. You may functionally, the simulator can give you the correct functional result from an ISA point of view for what the program would output. But the simulator can be inaccurate in terms of timing. It would say this program would take 5,000 cycles to execute, whereas in real hardware that it tries to mimic, it would execute 500 cycles. In that case, it's inaccurate in terms of how it models timing. Why would it be inaccurate? Well, for example, in the state machine that the hardware actually implements, or hardware is going to implement, your add instruction may take 5 cycles, whereas in the simulator, you forgot to model one of those cycles. Right? You modeled as 4 cycles. Then you're inaccurate in terms of timing. Right? So these two are important considerations in simulator design. The third is also important, speed, how fast the simulator can actually execute, can actually model the execution. Of course, the faster, the better, right? That way you can do design space exploration. You can ask questions such as, so for example, you can do a simulation that models the add instruction as if it were taking 4 cycles. And you can do another simulation that models the add instruction as if it were taking 3 cycles for a given benchmark. So let's say this is add that takes 4 cycles. You run this program in your simulator and figure out how long, what is the performance of your processor if the add would take 4 cycles. And you would, of course, do it on an application. Let's say performance or execution time, let's say. Execution time of, I don't know, the MATLAB application, let's say, that you're simulating on your simulator. And you get an execution time while you're modeling add for 4 cycles with 4 cycle latency. And let's say you do another simulation. Now you change your simulator, change the modeling of the ad to 3 cycles, and the simulator tells the execution time of the program, if your ad were 3 cycles in your machine, would actually be, I don't know, 10% lower. Which means that if you design a processor that did the ad in 3 cycles instead of 4 cycles, you would gain 10% performance on this particular application. Right? That's the power of simulation. That's what you would like to do with a simulator. Right? You design a simulator that outputs how long a program would take, and then you tweak the parameters of the hardware within your simulator to see how much benefit you would get if you had optimized that parameter. Does this make sense? Now in this lab, you did not do this timing. You did just do the functional, but we will later do the timing. So this is what you would like to get from a performance simulator, basically a timing simulator. How much performance I can gain by optimizing a particular feature in my microarchitecture or in my ISA. In this case, the feature being how long should the ad take. So, okay, if the simulator is not really accurate, well, if the simulator does not model the ad correctly, first of all, functional accuracy, all bets are off, right? The number you're getting here may not be correct. Because the program is not doing the right thing. The simulator is not modeling what the ISA would do. Right? Now, if the simulator doesn't have good timing accuracy, now you're making a decision. Should I make the ad 3 cycles or 4 cycles? And the simulator says, if you make the ad 3 cycles, you would gain 10% performance. And if that's what you want to do, you design the processor such that ad is 3 cycles. You put all the effort into that, for example. But if your simulator was not correct in terms of its timing, maybe this 10% number is not correct, right? For example, how could the simulator not be correct? The simulator is modeling the machine, right? A processor. In reality, your memory could take 100 cycles to access. Whereas the simulated memory, because the simulator did not model it accurately, was modeled as 1 cycle. Now your timing simulator is inaccurate in terms of memory operations. And all this number, these numbers you obtained in terms of the execution time of this MATLAB program is based on this simulated memory latency, 1 cycle. And you concluded based on the simulated latency that you would gain 10% performance if you made your ads 3 cycles instead of 4 cycles. Now that may not be the right conclusion if you had actually modeled memory correctly. Well, correctly meaning accurately in terms of what would the timing be. So if you actually go and model this as 100 cycles, what could happen? This program does a lot of memory operations, let's say. Okay. Then maybe the performance benefit you would get by making the ad 3 cycles instead of 4 cycles could be 0.05% in reality. Right? Why? Because the program may be doing loads, stores that access memory that have nothing to do with the add instruction. Right? And if the execution time of the program is really dominated by loads and stores, which means dominated by these memory accesses, and you're not modeling the latency of these accesses correctly, then you're missing out something important in your simulation in terms of the timing. And that could lead to a wrong conclusion in your design choice, right? Does that make sense? So it is important to get at least the important parameters, the simulation model, accurate in terms of timing, or accurate enough in terms of timing. Maybe you don't care if the memory takes 100 cycles or 99 cycles. Maybe you cannot model that exactly. Maybe you forgot. You don't model everything, because if you model everything, then you're really down into the hardware, right? Then you lose something else, speed, right? If you're really modeling every single gate in the machine, every single wire in the machine, the simulator will run like a dog. So you won't be able to run big programs to make these conclusions. So the goal in simulation is really to make the design decisions, right? What kind of design decisions? Oh, the other chart. That's right.
In the box.
In the box. There you go. You like this better? So I'll do this. Well, this yellow one doesn't seem to. Okay. Nor use one. So your goal in simulation is really to guide the design decisions. And you want to make the design decisions correctly. That's why these two matter. Do I add a cache to my design? Do I not add a cache to my design? Do I make the add 3 cycles? Do I keep it at 4 cycles? Do I don't know, try to optimize memory latency, for example? Try to reduce it somehow. All of those design decisions you can make via a timing simulator. You run the simulator with the workload you care about without the optimization, get the performance, execution time of the machine, modeled execution time, and then with the optimization, get the modeled execution time, and make a design decision based on the performance gain you would see. Let's assume your target is performance. So your model needs to be correct enough. The second thing is, well, you want to make the design decisions fast, right? The simulator gives you a result in 3 months. That may not be useful, right? If you can make this design decision very quickly, then that's great. That's why your simulator needs to be fast. And there's usually a trade-off between accuracy and speed. So if you model everything, every single wire in the machine, then your speed goes down, accuracy goes up, but your time to make the design decision becomes slower also. So simulator design is also kind of an art. It's a balance between these two. And sometimes you forego accuracy, usually it's timing accuracy, to get to the design decision fast. Because what you really care about at early point in design is what are the big things that you should add to your processor to make it faster. Okay. And you would like to get those big things correct enough. Okay. Usually functional accuracy you do not compromise. But there are cases where you might even want to compromise functional accuracy also. I will not get into this, but think about common case design. We talked about this last time, right? If an instruction that you really know doesn't occur frequently, and you know that your design will not optimize for that, in your early stages of the design, you may not want to model that instruction. Then for those programs that use that instruction, too bad. Your simulator will be useless. Okay. But if you're really certain that that instruction will not happen in the field, you're not optimizing for it, your design point is not that instruction, then you save time by not modeling that instruction. That's one example where you forego functional accuracy for speed as well as for designer productivity. Make sense? So the simulator you designed, well, is actually an example of this, except it's an example of the functional accuracy versus speed trade-off. And some of you either intentionally or unintentionally made that trade-off because we didn't really optimize it as we didn't really specify that as a criterion. So there's a variety of execution times, at least for this particular program. Okay. Okay, now let's move on with the lecture. But this is also part of the lecture. Right? This is also part of computer architecture. Actually, this is a very big part of computer architecture because a lot of what computer architects do when they're designing a machine is really simulation. Because you cannot build hardware for every single design choice you can make. Right? Think about building a Verilog design, not even hardware. An RTL level design for every single design choice you would like to make. It's impossible. Right? Do you build 10,000 different versions of machines in Verilog and try to figure out which one is better. It's impossible. Well, it's possible, I guess, if you have enough time. Everything is possible if you have enough time. But you have a time to market for your processor. And within that time, you have to make that design choice. So you cannot really build hardware. You cannot really design Verilog. You have to do high-level simulation. You have to do design at, I don't know, C or Java level simulation that abstracts the machine in some way, that does functional and timing simulation. And you do design space exploration here. Do I add a cache? Do I not add a cache? How big should my cache be? How many ways should there be? How many instructions per cycle do I process? How many cycles should that take? All of those design decisions you do here. And then once you're comfortable with things, you go and build the, I guess I'll call it the RTL level design. And then you do some optimizations at the RTL level design as well, like critical path optimizations and some other design decisions, but they have to be less global than these decisions, because this is much slower and also much more accurate, hopefully, because you're already informed by the time you do this design space exploration. Okay. And then once you are done with this, then you go and actually build hardware. And if you take a VLSI course, you do some of these steps, right? Well, I don't know if you build hardware in the VLSI courses here, but some VLSI courses actually lead to hardware. Okay, whereas at the architecture level, we're here, really. Okay? Okay, let's move on to other announcements. Well, you already know this. Lab 2 is due on the 17th, and you're doing an RTL level simulator for that, the single cycle microarchitecture. And you know the extra credit assignment, so this is just for your information. These are the readings that you did for today, and hopefully you brought your handouts from last time, because we will cover those today. And this is the reading for next lecture. Next lecture we will definitely start pipelining, unless we come up with some other new questions today on our dynamic events. This is one lecture that I would strongly recommend you to attend. It's on Oracle's newest processor, UltraSpark T4. It's going to be given by Dr. Jared Smollens, who got his PhD from CMU actually in 2007, and he's been working with the UltraSpark team, performance modeling team. So he's intimately familiar with all of these design decisions, and he made some of them for the UltraSpark T4. That's the title of the talk, a highly threaded ServoNet chip with native support for heterogeneous computing. He will go through the design, as I understand it, and tell you what the processor does. So I think it will be an interesting talk and it would be beneficial. It's at 4 to 5 p.m. You guys know where CIC is, 4th floor. This is the conference room. So that's what he will talk about, microarchitecture of the newest processor that has 8 cores and 8 hardware threads in each core. This is some concept we will cover later on. You can actually have multiple threads sharing hardware resources within a core and executing concurrently. Out-of-board execution in each core. This is like a sin for Sun. Sun was one of those companies that did not have an out-of-order processor for a long time. I guess this could be their first out-of-order processor. Is that true? I think it may be true. Yeah. But now it's not Sun anymore, it's really Oracle. So and basically a bunch of other design choices. So I would strongly urge you to attend this because you will really benefit from it, I think. Even though you may not know exactly all of the concepts, you will get a good idea of what a modern machine looks like. And finally, one of Sun's machines is modern. Okay. Last lecture, we finished single cycle microarchitectures. Oh, I'm being recorded, so. But that Sun doesn't exist anymore, so that's good. So, last lecture, we finished single cycle microarchitectures. We talked about microarchitecture design principles that I will remind you of again. We talked briefly about basic performance evaluation, and we started the microprogrammed machines. So let me test you on some of these. What does it mean to design for the common case? Or we call it bread and butter design also. Yes?
You should try and design for the operations that are a lot, so the ones that are continuously occurring, because you're optimizing those, then the general case is going to be faster.
Exactly, yeah. So basically, design your processor for the things that really take the most amount of time. For example, well, we kind of covered this here. If your memory is taking most of the time here, you shouldn't be optimizing your ad. Okay? That's kind of what it means. Design it for the common case. If your memory takes 90% of the execution time, well, focus on that. That's the most commonly occurring thing, probably. Of course, you need to determine that 90% of the execution time correctly, right? If you're misguided in your decision of what is the common case, then you're designing for the wrong thing. So you should be correctly guided in your decision of what is the common case. And then common case design makes sense. Then you optimize the common case, right? So in this case, your simulator may misguide you as to what is the common case. So you should design your simulator correctly so that you're correctly guided. Your workloads are also another thing that can misguide you, right? You have to pick your workloads correctly. The things that you care about, your design point, should constitute your workloads, but you need to analyze your workloads correctly so that you can figure out what is the common case, really. Right? For example, you could pick a workload that you care about, that you're designing your processor for, and you find that memory is the bottleneck. But you could also pick another workload that you also care about and find that ad is the bottleneck. So you have to actually have a good mix of workloads that tell you what are the bottlenecks that you should care about. And one way of going about common case design is taking a large number of workloads, and this is how design is done at large companies at Intel and AMD. They take a large number of workloads, hundreds, thousands. They simulate these workloads, analyze these workloads, and figure out what are the bottlenecks. Where does the execution time go? If the execution time goes 90% of the time to memory, like 90% of the average workload execution time goes to memory, then optimize that. That's the common case design. Okay. Another question. How does the single cycle microarchitecture make critical path design difficult? I guess what is critical path design? You should find and minimize your critical path, right? To maximize your clock frequency.
It's hard because if you have something really slow like that later where you can't like predict how long it's going to take, you can't cycle.
That's right, yeah. So remember, in the single cycle microarchitecture, your execution time is really determined by the worst case processing time of an instruction. So well, by that definition, it's difficult because now you need to optimize for that worst case. And if your worst case is very hard to optimize, as Sally says, it could be hard to optimize because your memory latency may be the bottleneck, right? You may not be able to speed up your memory because you may be bound by your technology. In that case, now you cannot make your cycle time smaller easily. The reason it makes critical path design difficult is now there's no common case. Your critical path is dependent on the worst case. And worst case may be very hard to optimize. Okay. And multi-cycle microarchitecture makes this easier because it decouples the worst case from the critical path. Okay. Remember the performance equation? How many people remember it? If I say, yes, two of you remember it. Why don't you make me write it then? So execution time is, if you remember it. Okay, number of instructions, good. Times something called CPI, cycles per instruction. Average, I'll call it. Yes, that's right. Basically, clock cycle time, right? So remember this is the execution time equation that we derived in the last lecture. I guess, how can you improve each component in a multi-cycle microarchitecture? So you can actually, the nice thing about this equation is you can break it down into three things that you can somehow independently improve. Now you can independently improve things in a these two because you have a multi-cycle microarchitecture, right? Your CPI is not always 1. Now your CPI can be long, but your clock cycle time can be short. There is certainly dependence, yes, that's right. But your average, remember the average CPI can be very low. How do you improve? Okay, I guess let's pick one. How do you improve CPI? Yeah, but you're not reducing the processing time in that case, right? You can go to your state machine, right? Remember the state machine? You had all these states. Maybe you can actually reduce some of those states by combining things with each other. Maybe you add more hardware to combine some of those states, right? You guys have the handout for the state machine, right? Or in front of your computer, on your screen. So remember what I'm talking about is that state machine. So you have a bunch of fetch states, and then a decode state, which we will cover today, and then a multi-way branch out of that decode state. Remember? Here you decode the instruction, and based on the instruction's type and opcode, you jump into a separate state to process that instruction. So your cycles per instruction is really determined by how many states you traverse through when you execute an instruction, right? Because each state takes one cycle. Well, some states do this. It's still one cycle. You stay in the same state. Right? And you remember why some states do this, because they access memory, right? If the memory is not ready, you're staying in that state. So you can reduce the cycles per instruction by merging states here, right? And if you can merge the states without significantly affecting clock cycle time, and you could do that by adding more hardware, right? If you're doing multiple different things, you can add more hardware, do those things in parallel, and put the states together, if it's possible, without lengthening your clock cycle time. So that's how you could reduce your CPI. Your clock cycle time, how do you reduce it? Well, that's more, you've got to go through your design, data path design, and control logic design, and reduce your critical path, right? One thing we did not talk about, actually we did not exactly talk about these two, but when we cover the multi-cycle microarchitecture, think about these. How can you improve it? What about this? There is this other component, right? The execution time of a program is determined by total number of instructions also. More complex instructions, that's right. But then that will affect these also, right? That's right. So these things are not totally independent. That's more complex instructions will increase cycle per instruction probably. Because now you're doing more things. Nope. You'll add more states here, right? Think about a repeat MOVS. You will add more states. But how do you improve this without affecting these? Let me ask the harder question. Compiler. Yes? Better algorithms. There you go. You guys are thinking in the right direction. Okay. Well, pipelining doesn't change the number of instructions that you execute, right? We didn't cover it yet, but it's a microarchitectural technique. It will change this. Actually, pipelining will change your average CPI, and we talked about this, right? Because now you're executing multiple instructions in a given clock cycle. You're increasing this I and keeping the C constant. So pipelining will reduce this. But if you change your algorithm such that it takes 1,000 instructions to do something instead of 10 million instructions to do something, you reduce execution time. If you change the compiler such that it eliminates redundant instructions, for example, compilers commonly do an optimization called redundant expression elimination. So they figure out what are the redundant things, or common sub-expressions, for example, and if things do not change, they can eliminate some of the instructions. So your compiler can reduce this. Make sense? So this is at a higher level in general. You cannot fix this problem at the microarchitectural level. Okay. So hopefully that gives you, well, I'm going to just flash these so that you're reminded of these three different principles. Critical path design, bread and butter common case design we talked about, and balanced design. Okay, we were at multi-cycle microarchitectures, and we're going back to it right now. The idea here was to determine clock cycle time independently of instruction processing time, and each instruction would take as many clock cycles as it needs to take. So we have multiple state transitions per instruction, and that's how it is, basically. Multiple state transitions per instruction. And this essentially translates to your state machine. How this is done is actually described by your state machine that describes your ISA. And we're going to implement the state machine. Okay, this is just as a reminder of the things that I've just talked about, so you can look at these slides later on. Okay, so we were looking at the LC3B microprogram multi-cycle microarchitecture, and we're going to continue to do that today. So if you have your handouts, you should probably take them out. And because you may not be able to see things well, although I'll try to optimize that. So this is the instruction processing cycle, and we were going to break this into multiple states for each instruction separately. And we will sequence from state to state to process an instruction. And we will specify the behavior of the entire processor as a finite state machine. And you remember we talked about what happens in a clock cycle. Control signals determine how the data path should process the data, and also what are the control signals for the next clock cycle. And you know why next clock cycle and not the current clock cycle. You don't want to lengthen your critical path. Just to remind you of the terminology, micro instructions, the controls is the name given to the control signals associated with the current state. Act of transitioning from one state to another is microsequencing. So we'll have a microsequencer that does this transitioning. Control store stores micro instructions for every possible state in the machine. So this is essentially store for micro instructions for the entire finite state machine. And the microsequencer determines what will be your next set of control signal, what will be your next state, what will be your next micro instruction, which means that what will be your address in the control store that stores the micro instruction for the next cycle. Right? And this is the visual representation of the machine. This is for LC3. You have a control and data path that concurrently operate in the same cycle, and they're connected. This contains the control store as well as a microsequencer, and these are the inputs to the control store. These inputs are essentially the information that's needed to determine the control signals that you will need in the next clock cycle. With this information, the microsequencer will determine an address into the control store, and the control store will be accessed to generate the control signals for the next state, and the control signals will be latched here so that they will be used for the entire next cycle. So this is your micro instruction. In LC3B, it consists of 35 bits. Some of those bits control the processing in the data path, and some other bits are only used to determine, partially at least, what should your next state's control signal be. And also, control takes some other information from the data path to determine what should your next state be. For example, is the memory ready? If the memory is not ready here, you might want to basically the finite state machine specifies that you should stay in the state until the memory is ready, so that the memory operation is complete. Or what is the current opcode? And we will see why you need this. Why do you need this? For example, if you're in this state, if you're decoding an instruction, your next state is dependent on what is in your instruction register, what your opcode specifies, right? And we will, actually, maybe this is a good time to power up the other projector so that you can concretely see what I'm talking about. that option is not available to me yet. So if you're in this state, decoding the instruction, the next state is dependent on the instruction register. Is it a branch? Is it an add? Is it a load bytes? Is it a load word? Is it a shift? Is it a multiply? So on, right? So that's a multi-way state. So the control, the microsequencer should provide a way of achieving this. At that particular state only though. Branch enable. Is the branch taken or not taken? Another control signal that determines what your next state should be. So this is your finite state machine. This is the LC3B finite state machine. No, okay. Okay. You guys can see. We covered these fetch states. I will go over them briefly again. This is how you fetch the instruction. And the state machine specifies in each state what happens in the data path and what is the next possible states, as well as what is the encoding for the state variables for that particular state. So this is state 18 as well as 19. And we will use this also as the address of the control store that contains the micro instruction for that particular state. So if you're in this state, data path performs these operations, and control figures out that the next state is 33. In this case, control is very simple, right? Because you have an unconditional state transition. In the next clock cycle, you always go to state 33. So how do you implement that unconditional state transition? Well, that's what the J bits are for. J bits are kind of jump, if you will. These are if you are unconditionally transitioning from one state to the other state, this is the encoding of the address of the next state. Make sense? So you have how many J bits? 6 J bits, because we have 6 bits to encode the state variables. We have 31 states, but we have 6 bits. You really need 5 bits, but we have 6 bits for flexibility of extension of the state machine for other reasons that we may get to do later in this course. So J bits here, the J bits specify 33. So that if you're in state 18, the J bits within your micro instruction are set to 33. So the person who is designing the control store sets those bits to 33, such that when you are in state 18, the next state is state 33. Make sense? And we will actually go and do some examples today as to how you would microprogram this machine, if you will. This is called microprogramming, writing the control store for this machine. Each micro instruction, each state. Okay? We were talking about this state. This is the decode state. At this point, your instruction register is loaded with data that you access from memory, which is the instruction, because you access memory with your program counter. And you look at IR 15 through 12, which is the opcode in LC3B ISA. So you should look at your appendix A, if you will, which specifies what is the opcode. So just to remind you, if you look at your ISA, bits 15 through 12 specify the opcode, right? Add is 0001, and is 0101. And in this state, what happened here? Somehow I pressed something. Okay, in this state, this is the decode state. Basically, microsequencer determines the next state based on this opcode. If your opcode IR 15 through 12 is 1011, well, these are actually undefined. So you go to some undefined states, if you will. So that's how you could, these states can take you to some particular code that you need to process if the machine decodes an illegal opcode, right? So I picked a bad example. We'll get back to that. So if your opcode is a branch, you go to the state that processes the branch. If you're, and we will get back to that also. If your opcode is an add, let's take the easy case. Then you go to a state that does the add. And once the add is done, this is the specification of the add. Destination register, this is what should happen in the data path in this state. Destination register should get source register plus operand 2. And operand 2 can actually come from two places, because there are two versions of the add. If you remember, we've looked at this before. There are two versions of the add. One, that's of R-type in MIPS, if you will. That takes two registers, and another that takes one register and immediate. And they're both handled in the same state, because they have the same opcode and you jump to the same state. Although you could have designed your state machine such that you would jump to different states, right? How would you do that? So you have, I don't know if I'll be able to do this, but can you see both of the handouts? I guess kind of. Well, maybe not. Okay. Say it again? Bit 5, exactly. So if you look at these two instructions, this is add, this is another add, and you can, well, all right, let's do this. These are your opcodes, they're the same for add with two source registers, and this is add register to immediate. They differ in bit 5. Right? Instead of having one state to implement both adds, you could have actually looked at bit 5 in the instruction register also and jumped to another state. Make sense? That way you would get the control signals for selecting between immediate and source register 2 from two different entries in your control stall. Okay, so your state machine is really your design choice. So there's nothing magic about the state machine. This is not the specification of the ISA. Right? The ISA only specifies what the add should do and what its encoding should be. Right? The state machine is the microarchitecture. How does the microarchitecture implement that ISA again? So in this case, we made the choice that you go into this state if your opcode is 0001, which is an add. And in this state, you have control signals to process the add. And next state is always 18. So you're done with the add once you do this. So what does the add do? So basically, this operation here is essentially specified in the ISA, right? This is your add. Operation is this. If bit 5 is 0, destination register should be set to source register 1 plus source register 2. Otherwise, destination register should be source register 1 plus sign extended immediate 5. And then you also set the condition codes. Remember the condition codes? LC3D has condition codes. And how do you set the condition codes? Well, ISA specifies that also, right? There are 3 condition codes, negative, 0, or positive. The condition codes are set based on whether the result of the add, which is whether the value in the destination register, is negative, 0, or positive. Make sense? That's the specification of the ISA. So this finite state machine specifies that should happen in the data path. And your control should provide the right signals. Now, what are the signals dependent on? Well, that is dependent on your data path design too, right? And this is our data path. Well, I guess we need to zoom out to see our data path. Okay, so this is our data path. So you need to provide the ability in the data path to be able to process that instruction, just like we did for the single cycle microarchitecture, right? This data path provides the ability to process all the instructions. So to process that particular state, what do you need? You need to have the ability to be able to source the register file, right? With source register 1, source register 2. And we have that ability here. You have inputs. I don't know if you guys can see it, because I cannot even see it. Is it visible from the back? Look at your handouts based on what I'm pointing to here. This is where an overhead projector, old style, would help. And I do have those transparencies too, but I guess we don't have the projector. So you have the register file, source register 1. If I can see it. Say it again. Oh yeah, there you go. Source register 1, you're right. Here it is. I was looking at here. Source register 1, 3 bits to specify which register it is. Because you have 8 registers in LCD. And source register 2, 3 bits. And destination register also. So you have the ability in the data path to select between source register 2 and also a sign extended 5-bit immediate coming from the instruction register. Bottom 5 bits of the instruction register. Well, why? Because the immediate comes from the bottom 5 bits. If this bit is 0, if this bit is 1, steering bit. Remember, we discussed this. Steering bit determines the interpretation of these next few bits in an ISA. The steering bit, bit 5 is 1. Then this immediate 5 should be selected to be operated on in the data path. So in the data path, you have the ability to pick between the immediate, sign extended immediate, coming from the instruction register, and source register 2. And this mux is controlled by that steering bit, right? And what is that steering bit? Bit 5 in the instruction register, right? We haven't shown you here all of the control, but that's bit 5. Bit 5 determines whether or not you pick the immediate. Make sense? So in that state, this bit 5 determines, bit 5, if you will, is a control signal that's generated in the data path, right? It's not stored in the control store. It's really generated in the data path. This is an example of hardwired control, if you will. You could have stored it in the control store, right? If you actually had a separate state for add register versus add immediate, you didn't need to take that bit from the instruction register, but you could have stored it in the control store. But in this case, there's no need to store it in the control store, right? Because it's only 1 bit. And you already have it available in the data path in the instruction register. Does that make sense? Okay. So we have the ability to now select between immediate and register. So these two flow into the ALU. And ALUK is, again, another control signal that's coming from the control store in this case that says, ALU, do the add. Right. So for this state, let's go back to the state machine. For this state in the state machine, ALUK bits in the micro instruction should say that ALU should do the add. Right? They should be encoded such that they would specify an add. And we will do the full encoding for some of these states very soon. Does that make sense to everyone? Okay. So the control store provides these ALUK bits. Now addition is done in the same clock cycle. The result is available at the ALU. Now also the state specifies that the result should be written into the destination register, right? And also a condition code should be set. So let's figure out what in the data path enables this. Well, how do you load ALU result into the destination register? Remember, it's a single bus design. What we need to do is to take the result, gate it onto the bus, which means that this gating signal, gate ALU signal, should be set to 1 in the micro instruction in the control store. And all other gating signals anything that could load data onto the bus should be set to 0. That enables the ALU result to be gated onto the bus and flow through into the register file. And we also need to write enable the register file. That's the load reg signal. So load reg signal should be set to 1 in this particular state. And destination register should be selected. Well, the destination register actually comes from, this is not shown here, but there is an additional data path element that's not shown in that data path picture. Destination register can come from 2 places, either instruction register 11 through 9 or destination register 7. And this DRMUX selects what is your destination register ID. And why? Well, because there are some instructions that specify their destination register in bits 11 through 9 in the instruction register, instruction encoding, which is add. That's what you should select in that state, right? And there are some other instructions that implicitly specify their destination register as register 7. And you guys will tell me what those instructions could be based on your knowledge of MIPS. It's not register 7 in MIPS, but it's register 31 in MIPS. There you go, right? You have a jump and link register, right? Which stores program counter into register 31 in MIPS. Well, you have something similar in LC3B ISA. Well, you cannot see the instruction itself up there. It's called jump to subroutine. A lot of ISAs are similar. Basically, the way it's specified is, well, let's look at JSR. And JSRR, there are 2 versions of it depending on the addressing mode. They have 2 different addressing modes. Jump to subroutine, they have the same opcode. They differ in this bit 11, which will change our state machine also. But the one thing it does is, this instruction does is it takes the program counter and stores it into register 7. Why? Because it's linking, right? You're jumping to a subroutine, and this is the next address of the next instruction. And if you look at this, this little sign here, it says this is the incremented PC. So it's really the address of the next instruction that's going to be stored in register 7. That's your link register. Make sense? So that's why you need that data path element that picks between, that picks the destination register ID either from register 7, hard-coded, or instruction registers bits 11 through 9. And this is your control signal that is stored in the micro instruction in the control store. If your state is a state where you're actually writing into a destination register and your destination register comes from those 3 bits in the instruction register, then you'd better set that DRMUX signal such that it selects those 3 bits, right? So in this state, the DRMUX signal is set to, I guess, 1 in that case, or depending on your encoding. Does that make sense? Is everything clear? Okay, we will go through, I think, would it be useful to go through and do the microprogramming of an entire instruction? Or do you guys know everything right now? No? Yes? Oh, do microcoding. Some people want it. Okay. I think that would be useful also, yes. Okay. So what should we go through? I guess let's pick an instruction. I guess I'll ask you these questions later. Let's go through the flow of an instruction first. But I would like to go through the microsequencer before I do that. Now that you're familiar with the data path, somewhat, at least not all of the portions of it perhaps, but you know how the data path operates in a single cycle architecture, microarchitecture. It's a little bit different here. because you have a single bus design and you can load the bus with the gaining signals. But other things, for example, here, this is how you compute the address. There are multiple ways of computing the address, and depending on the instruction, you pick some bytes, some bits in the instruction register, sign extend them, and add them to something else, if you will, program counter, for example. Actually, let me go through this JSR and JSRR a little bit, just to show you how that address is computed, since we were on that. So there are two versions of jump to subroutine. One version, JSR, an instruction is a JSR if this bit is 1. That's why the ISA specifies if bit 11 is 0, then program counter is simply the base register. Well, in this case, it's this one, right? And you basically, this is like jump register, jump and link register. This is like JALR in MIPS, right? The second one here, JSR, addressing mode is different. If bit 11 is 1, then the program counter is simply program counter, incremented program counter, plus this offset, sign extended to 16 bits, and left shifted by 1. Why left shifted by 1? Because LC3B is a word aligned machine. So alignment is at the word level. It's word. You're really jumping to a word, because each instruction is 2 bytes, if you will, and one word is 2 bytes. There's no point in jumping to the middle of an instruction because instructions are word aligned. Make sense? So you cannot start an instruction and an odd address, if you will. You have to start at even addresses because each instruction takes 2 bytes. So this bit 11 specifies how you execute the instruction. So you need to provide data path elements. And if you look at the data path, there are ways to compute the different addresses, right? PC could come from base register, or PC could come from left shifted, sign extended PC offset. 11 bits. Which means that we need to have the ability to set the program counter to either one. So how can we set the program counter to left shifted, sign extend 11 bits? Well, looks like this is 11 bits, right? You take the bottom 10 bits, bottom 11 bits of the instruction register, instruction bits. This is selected by this address muck if we are actually executing that JSRR instruction in that particular state. And or JSR instruction, I think, yeah. And it's left shifted. You have a data path element that left shifts that value. And in this case, it's added to the program counter, right? So you need to take the program counter and add to it. So this mux should actually select this input, right? Not this input, because this input is coming from, I don't know, the register itself. So you have the program counter here, you have the left shifted 11-bit immediate, sign extend 11-bit immediate here. That is added, and that goes into the PC mux. Now we want to load the PC. Well, this control signal better select this middle input to the mux, right? So you set your control signal such that it selects this middle input if you're executing that particular instruction in that particular state. And what is that state? Well, remember, what were we doing? We were doing JSR, right? So let's figure out where JSR is in this state machine. Well, the good thing is, I was going to say it's alphabetically ordered, but it's not. So this is JSR, right? After you decode JSR, if your bits are 0, 1, 0, 0, basically you jump to this state. And 0, 1, 0, 0 is actually 4, state 4. Right? So your opcode actually corresponds to your state encoding. That makes the jumping easier. So your J bits are actually your opcode in this case. Make sense? The first thing we do here is we check, the first state is, what is IR11? If IR11 is 0, we jump to another state. If IR11 is 1, we jump to another state. Why? Well, there are different functionalities that need to be implemented if, depending on whether the instruction is a JSR or JSRR, depending on this bit 11 in the instruction register. If bit 11 is 1, which is what I just described, then you're in this state, which I just told you about. You set the control signals such that program counter is set to program counter plus left shifted, sign extended, immediate. And also you load the program counter into register 7. So you set some other control bits that take the program counter and load it to the destination register. And how does that happen? Well, you have a path from the program counter into the register file. You gate the program counter onto the bus. This gate PC signal is set to 1 in that state that we just looked at. And all of the other gating signals are set to 0. And you enable load reg signal. You set load reg signals to 1, which means that register file is right enabled. And now you need to figure out what your destination register is. So what is your destination register? Well, if you're in the state 21, your destination register is really register 7, right? Based on the specification of the instruction. So in your data path elements, which is one of the later figures to set your destination register ID, your DR mux better select this one and not this one, because these bits are not what you want in the JSR instruction. Okay? So we've covered a bunch of states now. So where are these? Let me cover how we actually sequence between these states briefly. Let's look at the control logic to do this. And we will get back to some of these questions later. So data path. Well, if you look at this data path, at any point only one value can be gated on the bus. You've seen this. The advantage is low hardware cost. There's only a single bus. Right? You don't have many wires connecting different things. There's only a single bus. Disadvantage, now you have reduced concurrency, which means that if the instruction needs the bus twice to do two different things, these need to happen in two different states. Right? And you've seen this before. Okay. So we've seen this. We've seen some of this. These are the total list of data path control signals, some of which I've talked about. Okay, I'll skip these questions for now, but let's take a look at the control structure now. I'd like to go through microprogramming after I describe you what the control structure is. Because you have to, some of the bits in your micro instruction, remember, also determine what your next state will be. So you need to know the control structure before you decide what your control signal should be. There are three components: micro instruction, control store, and micro sequencer. And those three components are here. Well, not fully there. Okay. Micro instruction I've already told you about. These are the control signals that control the data path and the next state. Control store, I already told you about also. Each micro instruction is stored in a unique location in the control store. It's a special memory structure. Unique location, what is it? It's the address of the state corresponding to the micro instruction. Micro sequencer determines the address of the next micro instruction. So this is your, this is what implements the next state logic, if you will. So this is your micro sequencer. This is one design. Again, this is a microarchitectural component. And this is one particular design. You could have designed it in a different way. This is one of the lean or more compact designs, and you will appreciate it. Of course, the design of your micro sequence is also dependent on your state encoding, right? How you encode your states. What are your state variables? So let's start with one thing. Address of next state. This is what you want from a micro sequencer. Well, this is your control store. first of all. Let's start with your control store. Control store has the micro instructions. These are your 35 control signals as columns, and 64 states as rows, and each of them is the encoding, from 0 to all ones. And a micro instruction is a row here. Microsequencer determines what your next row will be, essentially. Well, let's go back to this microsequencer. How was that designed? If you look here, well, it starts with a mux. If IRD bit is set, let's say this is 1, this is the 1 input, then you select this as the address of your next state. If IRD bit is not set, then you select this as the address of your next state. So what could the function of IRD bit be? So what is this? These are the top 4 bits of your instruction register, your opcode. Right? So whatever, yes?
It says you're in the decode state.
It says that you're in the decode state, right? You either read the handout or you figured it out. That's good. Either way, perfect. It says you're in the decode state, right? Because what does this mean? You're basically determining your next state based on your opcode. And if you look at your state machine, there's only one. Well, let me do this so that's I don't need to go back and forth. If you look at your state machine, there is only one state where your next state is really dependent on your opcode. It's this state. And IRD bit, which is a control signal that's stored in the micro instruction, is set in that particular state, such that the microsequencer determines the next state's address based on the contents of the instruction register. Make sense? Which means that, okay, let's do some microprogramming. I don't know if you'll be able to see this. So this state is encoded as 22. Is that correct? 32. Yes, 32. Which means that this IRD bit should be set to 1 in state 32. So if we look at our control store, and I guess I need a pen to program this control store. I do have one. What is state 32? It's here, right? So this is the decode state. Can you guys see this? Okay. So that's your state 32. And you see that the first column here is the IRD bit. Well, this IRD bit needs to be set to 1, right? For your microsequencer to work correctly. And in all other states, that IRD bit is set to 0. I'm not going to go and do the zeros for all other states, but that's the only state where the address of the next state should come from those bits. For all other states, the address of the next state will come from that messy logic over there. Make sense? Okay, let's take a look at one other example. Let's say that we're in state 18. That's the fetch state. Our next state is state 33 unconditionally. How do you do that in this microsequencer? Well, obviously you're not going to select that input, right? Because that's dependent on the instruction register. It's not unconditional. The next state is not unconditional. So let's do the state 18 now. State 18. IRD bit is definitely 0 because we're not going to go to the next state based on the instruction register because we don't even have any logical thing in the instruction register. We haven't even fetched the instruction yet. So the next state will be 33. How do we get that? Well, we have only one option. These bits better be 33, right? Those 6 bits. So how do we enable that those bits are 33? That's the function of your J bits. And remember, J bits are part of your control store. That's, if you look here, these are the J bits, 6 bits. These tell you what is the next state if you're transitioning to that state unconditionally. That's the encoding of the next state. And we somehow need to make sure that we take 33 from here. So unconditional transfer. There are some states where we will do conditional transfers. And let me show you some examples of that. For example, our transfer will be conditional based on the ready bit of memory. Our next state will be determined based on whether or not the memory is ready, based on whether or not instruction register's 11th bit is 0 or 1. And why? We've just seen it, right? JSR or JSRR. Your next state is determined based on the 11th bit, because that's how you distinguish between those instructions. Based on whether or not the branch is taken. In this case, we don't care about any of these. We're really on state 18, right? We're unconditionally going to go to the next state, which is 33. Which means that we should set these bits, condition bits, that are also coming from our micro instruction in this particular state, such that they do not enable any of these. Right? Basically, the outputs of these gates should be all 0, such that J bits take effect. Because we are not branching on a branch condition. We're not going to the next state based on this condition, or this condition, or addressing mode. So how do we do that? So if you look at the micro sequencer, oh, there it is. Well, I want to actually go to the store here, control store here. So you see the condition bits here, right? We're in state 18. Unconditionally, we want to jump to state 33. And what is that? What is 33? 1, 2, 4, 8, 16. Right? So these are your J bits. 1, 0, 0, 0, 0, 1. And you want to go to that state unconditionally, which means your condition bit should be 0, 0. Right? Yes. Because if it's 1, 1, you would select IR11. You would jump to the next state based on IR11. So, okay, 0, 0. So these are the bits that control your next state. So we've just microprogrammed the control store for one state, state 18, from the point of view of the microsequencer. Now we can jump to the correct state. If we're in state 18, IRD bit is 0, condition bits are 0, 0, J bits are specified 33, and your next state is 33, unconditional. Now let's do the other bits for this particular state. Now that you know microsequencer how it kind of operates. Okay. So how do we do the other bits? Well, what else happens in this state? Let me pick something else here so that we can maximize the parallelism on the screen. I don't know if you can see that, but hopefully you will be able to. Or maybe this is better. There's a state machine here. Can you guys see this? Yeah? Okay. So, what is... So what else needs to happen in this state? We want to take program counter, place it into the MAR, and we want to increment the program counter. Okay. So let's see how we can do that. We have to go back to the data path, right? So how do we take program counter and put it into the memory address register? Well, if you look at program counter, there's a path. We need to load it onto the bus. So gate PC signal should be 1, right? So I find in the control store the gate PC signal, and I set it to 1. And also, I find all of the other things that can possibly gate the bus, and set them to 0 so that we don't load garbage onto the bus. Right? So now PC is on the bus. Now we want to make sure that the right thing latches it, which is the MAR. So I want to set load MAR signals to 1. So, where is the load MAR? So I want to load the memory address register. I don't want to load the memory data register because I'm just putting the address into memory, right? Do I want to load the instruction register? Well, let's take a look. Well, obviously, I don't want to take the PC and load the instruction register with it. That makes no sense, right? PC has an address, not the instruction. So that is set to 0. Do I want to load the BEN? So BEN, we did not talk about that, but that's whether or not the branch is enabled, branch is taken. If you look at your handouts, there's a logic that computes BEN that basically checks whether the condition code actually matches the condition code specified by the branch. Let's not get into it right now, but this is actually computed if the condition code specified by the branch in IR 11 through 9 matches the condition code that's in the machine right now. So there's a version of branch that says branch if negative, and if the condition code is negative, then this branch enable bit is set. So do we want to enable this logic? No, we don't want to enable that logic, right? We don't want to enable the setting of that particular register. So we're going to program that control signal to 0. We're not going to load the branch enable register. We're not going to load the register file because in this state, we're not really doing anything with the register file, right? Look at the state 18. So load reg is also 0. We're not going to load the condition codes because again in this state we're not doing it. Are we loading the PC? Yes. Good. Which means that we need to load enable the PC load PC signal. Look, in that state PC plus 2 is written at the PC. Now let's make sure that happens also. So how do we make sure that happens? First, we need to load the program counter. Now what do we need to load it by? Well, again, we need to look at here, right? We zoom in a little bit. Now you can see it better. We want to take the program counter, incremented by 2. Why 2? Because each instruction is 2 bytes in this particular ISA. And put it back to the program counter. We've already enabled the PC. Now we just need to set this mux signal correctly. Well, what is the mux signal? It's not specified on this data path, but luckily there is a place that is specified if I can find it. It's not. It's in this appendix C. Well, you could assign any value to it, really, but let's go. Well, I guess here symbolic values are assigned. So, but let's say this is 0, 0. If PC mux signal is 0, 0, you select PC plus 2. Otherwise, if it's 0, 1, you select the data coming from the bus. Otherwise, you select the data coming from the address adder. Well, in this case, we're going to select 0, 0 because that's PC plus 2, right? That's the 0, 0 signal. Okay, so what are we going to do? We're going to set this PC mux control signal to 0, 0. Okay, what else? We haven't finished the control store micro instruction for this state yet. Well, DR mux. Do we care? We're not writing to the register file. So this is really a don't care, right? What is the DR mux signal, you may ask? We've looked at this before. So I will show you for the sake of completeness. Except it might have disappeared. Oh, I have many of these. That's the beauty of concurrency, right? It's wasteful, but you can accomplish things much faster. Well, the RMAX signal. That determines whether your destination register comes from IR 11.9 or 7. In this state, we don't care. We're not loading the register, destination register. So that signal, they don't care. Similarly, SR mux determines, SR1 mux determines whether your source register, one of your source registers, actually comes from IR 11 through 9 or IR 8 through 6. This is very similar to what you're going to do for MIPS, right? Remember? R-type, RT versus RS. yeah, your register source can come from either of those, right? So the underlying implementations are very similar. So again, we don't care because we're not going to, even if we source the register, we're not going to use it, right, for this state. So SR1 mux is 0. Address 1 mux. What is address 1 mux? So you need to look at the data path. Where is address 1 mux? You guys see it?
Yes.
It's in the center. There you go. Okay, good. Again, do we care? We don't care, right? We're not computing an address. So we don't care about all of these other elements that are not going to affect our output because we're not going to select the product or the result of the logic that they affect. So that means that control store entries here are all X's. MAR mux. Okay, this could be interesting. Where is MAR mux? Oh, there you go. Okay. I see. So in this case, again, we don't care because, oh, upright. I was looking at it. So zooming doesn't always work, huh? Because what I see is not what you see. MAR mux loads an address onto the bus. An address could be computed by this messy logic or by this messy logic. Well, we don't care because we're going to load the MAR with the program counter. Right? And program counter's loading of the MAR doesn't go through the MAR mux. We already set the gate PC signal. And we already set this to 0. Which means that, again, the MAR mux signal is a don't care. Similarly, we don't care what happens in the ALU. Some of these we will not discuss, but again, we don't care here. Actually, we will need to discuss when we get to memory. But we don't care about any of these signals. So that's your micro instruction for this state. Simple, right? It's fun also. So you micro-programmed one thing right now. So now your job is to fill out all of it. Is that fun? Okay, let's do some other states before we go into the rest. Okay, so now we can go to the next state. State 33. So state 33 you program similarly. I don't want to go into all of this, really. But what you need to do here is I will show you how the microsequencer operates. So let's go to the microsequencer. Now we're accessing memory in this state, right? And the next state is really dependent on this ready bit. Okay? So let's figure out what our control signals should be for the microsequencer. We've already figured out that in state 33, we're not decoding the instruction. So where's state 33? Okay, this is state 33. This is the state we're concerning ourselves with at this point. IRD bit is 0, right? Now the next state is conditional upon whether or not the memory is ready. So let's do that. Which means that your ready bit should go through here, and it should affect the output. Which means that your J1 bit better be 0. If your J1 bit is 1, your next state is not dependent on the ready bit. So we figured out J1 at least. What is J1? J1 is 0. And you somehow need to select your ready bit, which means that your condition 0 should be, condition 1 should be 0, and condition 0 should be 1. Okay. So let's do that 0, 1. And anything, well, the thing that's left is now what are your other J bits? Well, what are your other J bits? The next state is either 33 or 35. Well, bit J1 gives you that 2 difference, right? Difference of 2 because it's bit 1. So all your J bits can specify 33 again, right? Which means that if this ready bit is set, your J bits take into effect, all of your J bits. If this ready bit is not set, you stay in state 33. If this ready bit is set, your state, everything else specifies 33, but you just ignore this one and set this to 1. Okay, so your next state encoding is again 33 here. 1, 0, 0, 0, 1. Okay? And this way, you can figure out all of the other control signals. Basically, what we do again here is, now here we're accessing memory, which means that we need somehow, we've already put the address into the MAR. We need to somehow access memory, and there is some mess here that we did not really talk about, and I don't want to get into necessarily, but we will talk about unaligned accesses. You can read it in your handout. Basically, we want to enable memory. Actually, let's see, how much time do we have? Based on that, we could get into it. Okay, let's not get into it right now. We want to enable memory. So there's some logic that enables memory here. But this logic is really computed based on something else, which I will talk about later on. And what is that something else? Your MAR, memory address, goes into this address control logic. This is the logic that implements memory mapped I/O. So if your address is within some range, then you access memory. Otherwise, this memory address actually indicates an I/O device. Remember the memory mapped I/O? Your I/O devices can be mapped to a portion of your memory. This is the hardware that determines whether your memory access is actually an I/O device address or a memory address. Let's assume that it is a memory address. So this MIO enable signal enables the memory system, if you will. So in this state, since we're accessing memory, we want to enable memory I/O. Set that to 1. I hope I set the right thing. And we are reading from memory, right? We're not writing to memory. So this read-write signal should be 0. So if you look at read-write, that again determines whether we write to memory. Except there is a little twist to it because of word writes and byte writes. And unaligned accesses as well. So there is this additional write enable logic that takes the read-write signal and converts it into 2 write enables. Are you enabling the write to the top byte or the bottom byte or both? So you could think of your memory organized like this. You get a word alignments. And you could think of your memory as divided into 2, top bytes and bottom bytes. And you could have a write enable signal for the top bytes and write enable signal for the bottom bytes. So if you're doing a load word, in this case we're not storing to memory, so none of the write enable signals will be enabled because we have this read-write signal specifying a read. But if we were doing a store to memory, this write enable logic, what does it take? And this will be one of your homework questions to figure out what this write enable logic is. But the idea is, if we're writing to memory, we look at the data size. And what is the data size? That's specified by the instruction again. Are you writing to a byte or to a word? In LC3B, there are 2 data sizes. You write to a byte or a word. And then you also take this bottom bit of this magic thing here. What is that? Memory address register. Why would you want to look at the bottom bit of the memory address register? Exactly. That tells you which byte you're going to write to, right? So if you're doing a load bytes, actually I don't think LC3B gives you the ability to write to an unaligned word address. But let's do the byte case. So if you're going to write to a byte, top byte means that your address, this is a big endian machine. No, it's a little endian machine. top byte means that your bottom bit of your MAR is actually 1. Bottom byte means that bottom bit of your MAR is actually 0. So if you're writing and bottom bit of your MAR is 0, and if this is a load byte, and this is a byte operation, then write enable 0 signal is 1, and write enable 1 signal is 0, right? Because you're writing to the bottom. If you're writing, and if this is a byte operation, and the bottom bit of your MAR is 1, which means that you're writing to the top byte, then write enable 1 is 1, and write enable 1 is 0. Make sense? So this is logic that determines which write enable, which byte in a word will be written by a store instruction. And note that you cannot store these write enable signals in your control store. Right? Because these write enable signals, these are control signals, really. These are controlling what portion of the memory should be written to. You can say, I would like to store this in my control store, but you cannot, right? I guess you could, and I'll let you think about how you could. But these are really dependent on your address, right? The address that the instruction generates. So it's a lot more efficient to figure out these control signals based on some control signals supplied by the micro instruction, which is this read-write and the data size, in addition to the bits coming from the address, and figure out which bytes you're going to write to. This cannot come from the control store, at least as we specify the microsequencer and the control line. Does that make sense? So there's always this trade-off between, do you actually generate these signals in hardwired logic like this, or do you store them in control store? I'm going to claim that you can actually store these things in the control store, but you have to change the machine design significantly. So if you're interested, you can think about it. But if you're not interested, don't think about it. Understand what you have at hand. You can design a separate control store where you can get these signals from. But it's going to be very messy. So it's a lot easier to generate these two signals in hardware with some signals from the control store and the address. The reason it's a lot easier because they're dependent on the address that you generate. And the address, you do not know until you compute it. Right? And you compute the address at some state. Right? Now you could use that address to index the control store. Right? That's how you'd actually get those bits. But you could use that bit actually to index the control store also. Okay? But then it becomes complicated if you think about memory map I/O. It may be easy here. It'll become complicated with memory map I/O. Okay. So let's finish the control signals here then. Data size. Well, data size, we're loading an instruction, which means that we want to load the entire word, right? We're not going to load a byte. I assume, I don't know what the control signals are essentially, exactly, but let me figure out. Where is the data size control signal? Oh, there you go, data size. So if you look at this, data size could be a byte or a word, and it looks like byte is 0 and word is 1. So I'm going to go with that convention that we established. So I'm going to make word 1. And left shift. Now I have no idea what this control signal was. Left shift 1. Did you guys see that? Oh, I see. So that's the address computation enabler here. That's left shift, right? So whether you actually left shift the address or not left shift the address, in this case we don't care because we're not using this path, right? Well, we're not loading any address. Right? Does that make sense? So in this case, this is 0. Okay? So what about the other control signals? Well, we're dealing with memory in this state, right? To remind you, basically this state is accessing memory. So really there's nothing else going on in the other parts of the data path. In a sense, this instruction is just, not instruction, the state is confined to things that are happening here. You're waiting for memory to output data into this memory data register. Right? And I ignored some of this logic, but you can think about it. Think about what's happening here. So everything else that's going here, we don't really care as long as they're not going to affect state. So what do we do in that case? Well, we're going to set all of the load register signals to 0. And gating signals, again, we don't care, right? Because we're not loading any registers. We could be gating stuff on the bus. And we could be gating garbage on the bus. Nothing bad will happen. PC mux, we don't care, because we're not going to use any of these signals to affect state at all. And hopefully this will give you an idea of an inefficiency of this design, right? Let me look a little bit forward at this point. So this state, what state were we in? We're accessing memory, right? Okay, we're accessing memory in this state. Only this part of the machine is active, right? Only this part of the machine is active. And you're waiting, I don't know, maybe 100 cycles to do this. This part of the machine, we've set the control signals to don't care as long as they don't affect any of the registers. Well, you're kind of wasting all of this hardware, right? So maybe you could add some more things to enable this hardware to do something else in parallel while you're accessing a memory. Maybe you could pipeline the operation of different instructions. While one instruction is being fetched here, accessing memory, an earlier instruction may be using the ALU, doing something else. And that's the idea of pipeline. That's one downside with this design. You have this hardware, but you have the state machine that operates on only portions of the hardware at any given point. And some of the hardware is kind of wasted. And the idea of pipelining is, oh, we have all this hardware, and some of this hardware is used for, in a confined manner, for different stages of instruction processing. So why don't we add some other stuff to this hardware such that while one instruction is in its fetch stage of processing, another instruction is being decoded. And while that's being decoded, another instruction is actually being executed in the ALU. Of course, you need to ensure that these things do not affect each other, right? Because these are separate instructions, so you need to add additional hardware. That's the idea of pipeline. We're going to make this design more efficient later on. But first, you should understand this design completely. Okay. Okay. So now you know how to microprogram the machine. Right? You know at least two states fully specified. You can specify some other states. And that's what you will do in your homework for a simplified, much more simplified version. But we will probably give you this version to microcode for something else later on. Okay, let me go back and go through some of these questions. How many cycles does the fastest instruction take? Well, the state machine tells you that. What is the fastest instruction? If you look at it, all instructions go through these fetch states and then the decode state. And if you look at, let's ignore RTI first, because that's not implemented here. The fastest instruction really takes one cycle of execution. You go back to 18. So 1, 2, 3, 4, 5 states, well, depending on your memory. If your memory is 1 cycle, then 1, 2, 3, 4, 5 cycles. If your memory is 100 cycles, 1, 101, 102, 103, 104 cycles. That's the fastest instruction. But not all instructions are the same. For example, this instruction, one memory, I guess 1, 2, 3, 4, 5 cycles plus 2 memory accesses. Okay. And that's, I don't know, that's the trap instruction, if you will, here. There are a bunch of other instructions, 4 instructions also. Okay. how many cycles does the slowest instruction take? You can go and figure this out based on the state machine. And I would encourage you to answer some of these questions. And maybe there will be some homework questions as well. I'm not going to go into all of these, but you should be able to figure this out relatively easily. Why does the BR take as long as it takes in the finite state machine? So here's your BR instruction. We have a separate state here that tests the branch condition. Any idea why? Why not do that computation here? Well, we do the computation here, right? Branch enable. Basically, even before knowing whether or not the instruction is a branch, you figure out the branch condition here and set the branch enable bit. And how do you set it? Basically, if you look at the branch, very quickly look at the branch instruction. This branch is based on the condition code, and it's specified exactly here. This is your opcode and ZP bits. At any given time, you could set any of these, and basically, this tests the condition code, right? The condition code specified by the state of bits 11 and 9 are tested as follows. If bit 11 is set, N is tested. If bit 11 is clear, N is not tested. Meaning that if bit 11 is set and the condition code N is set in the machine, the branch is taken. Okay? Because the result was negative. That's what the condition code means. And the branch is testing if it's negative. Or if the Z is set and the condition code Z0 is set. Or if P is set and the condition code P is set. Then we take the branch. So if you look at the state machine, this computation is done while we're decoding the instruction. We could have moved that computation here, right? Because we don't know whether the instruction is a branch yet. Make sense? We enabled load BEN here instead. Why? Well, because we don't want to lengthen the critical path in the state. In this case, you can argue that this is a simple computation, and I would agree. But this is just to illustrate that you can move, you can do some computation early, even though the instruction doesn't require it. This is the concept of speculative execution. We discussed this, right? Doing something before you know it. Before you know, you will need the results. In this case, the data path element, load BEN signal, branch enable signal, is set based on this computation. Even though we may not need it, even though the instruction may turn out to be an add, right? But we do it before so that you don't have to do it in this state. In this state, we just test if BEN is set, and if it's set, you go. If it's set, you compute the program counter. If it's not set, then you go to the fetch state. You go to the next instruction. Make sense? So you could do computation at different places. The reason the branch condition is set in the previous state, in the decode state, is we don't want to lengthen the critical path necessarily here. Now you could argue that you could do another thing, right? You could have said, oh, this state is kind of useless. Why didn't we actually check for BEN here? You could change your state machine, right? You could say, instead of jumping just based on the instruction register opcode to the next state, I will also check BEN right here, because I'm computing BEN, and change the microsequencer design such that it also takes into account BEN here, whether the branch is taken or not. Well, that's going to be difficult, right? Because now you're taking, again, the same thing. You're doing computation here, and you're using that control signal to determine your next state. And if this computation is too long, you can lengthen your critical path. And again, it's not only that, but you take this into account only if your instruction register is something. Okay? So you need to even check for that. Only if your instruct opcode is branch. So these are the trade-off as an architect you need to make. Okay, I think we will pick up from here next time and hopefully we'll move into pipeline.